Welcome back to our video lecture series on Chapter 11. We're going to talk about energy changes tonight. So when we talk about those phase changes, going from a solid to a liquid to a gas, what we find is that this ends up taking energy as we change phases. And it either takes energy or gives off energy depending upon the direction that we're going. So for example, if we're going from a solid to a liquid, this is going to require energy. So we have to take the solid and we have to add heat energy to turn it into a liquid. But if we go the other direction, that's going to give off energy. And so we're going to see two types of curves tonight. We're going to see heating curves and we're going to see cooling curves. So in this heating curve, what we're seeing is we start here in this sloped part of this graph. And what this is saying is that the temperature change, that the temperature is changing. Because once we get to this point where the slope is 0, we're seeing all of the energy go into that melting process. Then once all of the solid has turned into a liquid at its melting point, then the energy that we're putting in, that heat that's being added, goes into turning that liquid into liquid at its melting temperature to liquid at the boiling temperature. Then what happens is your energy goes into turning the liquid at the boiling temperature to a gas at the boiling temperature. Now, right here where we see this sloped part for the gas, that is one of the reasons why a burn from steam, like water in its vapor state, is so much more dangerous than boiling water, because gaseous water can get higher than 100 degrees Celsius, so it can burn you even worse. So when we start looking at this, it's really hard to kind of visualize what's going on. So I'm going to show you a little animation in class of what the molecules look like at each point here. And in this video, we're going to try and focus on the math part, and then we'll work on the conceptual part in class. And so overall, what we're going to see is an overall change in, where you're starting and where you're ending up. And we're going to be able to calculate the overall heat added. And the key is the parts that I've highlighted in yellow, where you're seeing a slope, these sections are going to use your typical equation that you're used to seeing, Q equals ms delta T, that you saw from chapter 6. The only issue now is that S will change based upon what state you're in. So for example, when we used 4.184 joules per gram degrees Celsius for the specific heat of water, that was the specific heat for liquid water. But solid water and gaseous water have their own specific heats. So S will change based on the state the compound is in. Okay, so then the kind of new equation is honestly not even really equation. I don't even really like to call it an equation, but it is Q equals, let's say, mass times delta H. And the reason I don't like to call it an equation is because sometimes your delta H might not be per gram, it might be per mole, and then your Q would be mole times delta H. And so this just depends upon the unit. On the unit delta H is in. And what I mean when I say this depends upon the unit, I mean what you're multiplying delta H by. And we'll see an example of this in a couple of moments. So what we're seeing in our heating curve, right, is that our temperature increases, and as a particular phase is warmed, and then during that phase change, the temperature is constant. So we have a constant T. Oops, hold on. Oh, darn. Okay, that's better. During phase changes. So, the other thing is that we're going to see those sections of the graph where we have that kind of flat zone where the slope is 0. That section is going to have a delta H associated with it, and that delta H is going to also change based upon if you're doing vaporization, right, or melting. So there's a lot of words in here that I'm not gonna talk about right now, that we can talk about and kind of point out as we do some problems during class. Let's look at a cooling curve, and then I think we'll move on to a problem. So when we look at a cooling curve, it's the same as a heating curve, just the opposite. So instead of heat being added, heat's removed. And one of the things that you might have noticed about both of these graphs is they had that little like indentation right there, and in the other graph there was an indentation, I guess not really an indentation, a little extra bump. Those are called supercooling and superheating. They're unusual phenomenon that I will talk about more in class if you care to know a little bit more about them. So supercooling is just kind of wild. It's where your liquid cools below its freezing point, and then like you like jiggle it or wiggle it or something, and then boom, it freezes. It's just crazy. So I don't know, it's just fascinating. But you know me, I love chemistry. So let's talk about kind of the math behind this. So what we're seeing is a variety of delta H's in our heating and cooling curves. And when we look at those parts of the curve where, if I kind of draw a quick one here, where our slope is constant, right, those two parts, these are our phase changes occurring at constant temperature and constant pressure. And so these are expressed as delta H's. And so when you look at delta H, there's going to be, oh wait, did I do that wrong? Wait, hold on. Delta H, my brain stopped working. Oh no, yeah, I did it right. Yeah, I just got confused because there were 3 down here, but only 2 parts that I highlighted in that graph. But then I didn't read it and saw the sublimation. Okay, so molar heat of fusion is your delta H for this part of the graph where you're seeing melting happened. And then your molar heat of vaporization is your delta H for this part of the graph where you're seeing a liquid turn into a gas. And so not everything sublimates, and so if something sublimates, it would have an additional delta H, and that would be the molar heat of sublimation. Notice how I've defined molar heat down here as the heat absorbed when 1 mole of something changes phase. And so these delta H's are all going to be either per mole, or sometimes they'll be per gram. And what you're going to find is that turning something into a vapor takes a heck of a lot more energy than melting something. So you're going to see your delta H of vaporization is going to be greater than your delta H of fusion. And then taking something from a solid directly into a gas, which is sublimation, is also going to take a boatload of energy in comparison to a delta H of vaporization. So again, what is this energy even describing? So this energy is talking about how much energy it takes to separate the molecules from each other, because remember, those molecules are attracted to each other with intermolecular forces. The stronger the intermolecular force, the more energy it's going to take in order to break those attractions and cause a phase change. So here I reference again that like equation where above I also said you could use Q equals the mass times delta H depending upon what the unit of delta H is. So N is an abbreviation for moles, and if your delta H is, joules per mole, then you're going to multiply it by moles to get your Q. But if your delta H is in, I keep writing delta H, joules per gram, then you're going to multiply it by grams to get your Q. So let's wrap this section up with a practice question. So how much energy is required to transform 350 grams of ice at its melting temperature to liquid water at 3.5 degrees Celsius? Honestly, my favorite way to start all of these problems is to draw a small graph off to the side. I like to draw the graph because so many times students don't know where to stop and start. And so if we draw a little graph and we know that this section here is when you have solid water, and then if we know over here you have liquid water, and over here you have gaseous water, and this part is the melting process, and this part is the vaporization process, then we can have a sense of where we are on the graph. And so we're saying that ice is at its melting temperature. Notice how it's saying the word ice, right? And so that means we're starting here at ice at its melting temperature. And we need to take that ice and turn it into liquid water at its melting temperature. Once we get the ice into liquid at the melting temperature, then we're going to heat it up to that 23.5 degrees. And so you just need a gentle reminder that ice has a melting point of 0 degrees Celsius. And so we're going to use two different equations here. This is going to be Q1 and this section is going to be Q2. So for Q1, you're going to take your moles or your mass times your delta H. And then for Q2, you're going to use MS delta T. Let's start with MS delta T because that one's really familiar to us. So for our Q2, we know our mass is 350 grams. We know the specific heat of water is 4.184 joules per gram degrees Celsius. And our delta T is T final 23.5 minus 0. Where did I get that 0 from? Well, it said ice at its melting temperature, and I know that the melting temperature of ice is 0. So then you can calculate that for Q2. Then the other thing that we need to do is we need to figure out what the delta H is for water when water is melting. So I'm going to look that up really quick. And you know what? You could do that too. Maybe it's in your textbook. Maybe you're Googling it like I'm about to do. So I am going to Google heat of fusion of water. There we go. Good old Google. Oh, Google. No, I don't want you to listen to me. So it says heat of fusion of water at 0 degrees Celsius is approximately 334 joules per gram. Ooh, and it gave it to me in per gram? Thank you, Google, because now I don't have to do more math, so I can do mass in grams. Oh, you know what? I'll write mass because I'm a good chemist. So 334 joules per gram is my delta H, and I'm going to multiply that by the mass I was given, and I'm going to get my Q1. So when you go through and you calculate these Qs, what do you do with them at the end? Well, you add them. So you want your Q total is Q1 plus Q2. So you'll go through, you'll grab your calculator, you'll figure out what the number is here, you'll figure out what the number is here, and add them together to get your final answer. So plan on practicing that a lot more during class. Thank you for your attention as always. Have a great night. Katoni signing out.